kind of review of this picture. Does this always work with learn from this graph? All right. So let's see. Can someone explain to me why it's 6 orders of magnitude from here to here? What's the size scale associated with QCD, with the proton? QCD, what is that in units? So some useful units. One Fermi. So about more of a size scale, right? Because the proton's a little bit bigger in a sense. The proton size is really set by the lighter, by the mesons in a sense. So that's a little bit tricky. Roughly speaking, it's a little bit bigger than its mass. What sets the scale of the weak interactions? So what is that in units? How many Fermis is that?
100 GeV.
Yeah, so it's 100 GeV. Well, a Fermi is like 200 MeV. And the weak scale is the Higgs wave 200 GeV. Factor 10 to the 3 in distance, 10 to the 6 in area. Now you've got to go through look at factors of 2 and pi and so on, but that's basically where that factor of 10 to the 6 comes from. It's just basically the ratio of a circle the size of the QCD scale to the circle the size of the weak scale. There's always a reason for things in science. That's why you went into science, right, as opposed to something else. There's always a reason. You notice the W and Z production, not surprisingly, therefore, are pretty close together. Just some factor of 2 because the W is charged and the W is complex and the Z is neutral, but roughly speaking, it's a factor of 2. Now, tops are interesting. Why are they down here? This is actually, in a way, a little bit misleading. They've placed the top part at its mass, which is 175. Really, to produce a pair of tops, you have to go out to 350. So really, in some ways, they should have put it here. Now, why is the ratio of W to top this order? Well, that's not so simple. Let's think about all the competing effects. First of all, it's easier to make resonance than to produce a pair of particles. There's some phase space. So you pay a price. You want to make QT bar versus W. And the particle distribution functions fall off very rapidly. So when I go from 80 GeV to 350, that's a substantial factor. And in fact, you naively guess it'll be way down here. But W has to be produced in QQ bar. Tops can be produced in glue goes to the TQ bar, and the glue particle distribution, glue particle luminosity is larger than the quark anti-quark luminosity, so that brings you back up. And top part production is a strong interaction process, whereas this is a weak interaction process, so there's a factor of alpha S relative to alpha weak, and that brings you back up. And that's where you're going. I haven't said anything about what's on this side. I want to remind you, this is for 14 TeV, so these numbers weren't appropriate quite last year. Well, they're not quite. What is this stuff? Well, at this luminosity, which was a little bit larger than last year, and pretty much is where we expect to be in 2015, this is the number of collisions per second. 10 to the 9, 10 to the 6, 10 to the 3. So 10 to the 9 collisions per second, that gives you that sort of 10 to the 15, 16 collisions per year that I mentioned. And that's kind of the rate. There are billion collisions per second, of which they can only store about 1,000 or so. Sorry, a few hundred or so. Close to 1,000 to be the maximum. So what's shown here is, this is how many events are actually going into the level 1 trigger. It's not all the events, but basically almost anything, any minimum bias event goes into the trigger, and then most of it has to be thrown out. Only a few thousand events can be moved on to the next level of the trigger. At Atlas, then, there are 2 more levels. CMS, there's only sort of 1. They don't actually operate that differently. And so this is a CMS plot. This is high-level trigger. So LV1 is level 1, HLT is level 2, and Atlas is HLT is level 2 and level 3. At Atlas, they literally have a level 2 and an edge filter. Okay. and then this is how much you can write out. So you notice that by the time you're at this energy and at this luminosity, you can't even write down all the W goes to lepton neutrino limits that you produce. You already have to throw some of those away. So, well, okay, that's an issue. And an interesting one, which they're fighting, actually, trying to figure out how to keep as many of these types of things as possible. Because if you start throwing out your W events, you start throwing out other events that maybe are important. You don't want to be throwing out leptons if you don't have to. But you have to throw some of them. Okay, so we'll get to more detail on that. All right, any quick questions? Or we just had a question session, so let's move on. Okay, now last time I mentioned a couple of QCD facts, and today I want to mention a couple more. So we have QCD for our purposes is a theory with 3 colors and 3 light quark flavors. And here are some properties of that theory which are not unique, to this theory, but on the other hand are not general either. One is the property of being UV free, without which we wouldn't be able to do perturbation theory for physics by scales, and the other is that it's IR confining, which means we actually had IR states. And the mass gap. There are no massless particles in this theory. The second, which Professor Tani emphasized in technical detail this morning, was this point about factorization. And I wrote it down naively last time, I'm going to write it down correctly this time, which is that the cross-section for producing something, plus lots of junk from the underlying event, and a little bit of this, and a little bit of that, is the integral of x for the 2 incoming partons of their parton distribution functions, which are functions not only of what fraction of momentum of protons they carry, but also an arbitrary factorization scale. And you have to multiply this by the partonic cross-section to produce the final state x at the parton. And that's a function of the product kinematics and also a function of the factorization scale. Now, if you compute it to all orders, the factorization scale dependence cancels out. In a perfect calculation, there is no dependence in the factorization scale, it was arbitrary. But a real calculation is done to a fixed order, leading order, next leading order, next leading order. There's always some residual dependence in this integral on UF. This depends on UF, this depends on UF. At any given order, the UF dependence will not exactly cancel. It's exactly the same as with renormalization scale dependence. You do a perfect calculation, of course, the normalization scale doesn't matter. The normalization scheme doesn't matter. The normalization scale doesn't matter. It's an arbitrary way of making sense of perturbation theory in a context where you have some fundamental problem with doing perturbation theory just off the get-go. How can you do perturbation theory in alpha S when alpha S doesn't exist? There is no alpha S. It's a QCD scale. The theory is a QCD scale. What are we doing? We're saying, well, the theory acts as though at some scale there's kind of an alpha S. So we'll expand in that. We have to remember, it was arbitrary. Right? Alpha S takes all values between between very small and very large. So we pick one that sort of allows perturbation theory to make sense. But it's arbitrary. That's true in the normalization context, and it also shows up here, where what we mean by the proton, what's in the proton, and what we mean by what's going on in some hard collision, doesn't have an automatic separation. You have to choose, and that's what UF is about. You are defining perturbation by choosing UF. If you don't pick up UF, you have no way to do the calculation. Perturbation theory is very subtle. You really have to think about it. But we couldn't do it at all if it weren't for this. Now, 2 other properties which are very special to QCD and not true in general. But one of them is this one. I went through the hadrons last time, and they have the property that all of them decay down, some very rapidly, some more slowly. They end up decaying down to basically kaons and avs and pi's. On the meson side, on the baryon side, we decay to neutrons and protons, and some of these guys are moderately metastable for it. But basically, that's what everything decays to. Why? Why do we have these guys down here? Why are they there? What makes them special? The pseudo-Nambu-Goldstone bosons, right? Because the quark masses are small, there are approximate global symmetries, which are spontaneously broken by the dynamics of QCD, and explicitly broken by the presence of the quark masses. If the quark masses were 0, then you'd only have the spontaneous breaking. You would literally have Nambu-Goldstone bosons, and these particles would all be massless. On the other hand, the masses of these other particles would barely change at all. The rho mass on mass has nothing to do with the up and down of the mass. It has to do with the scale of QCD. It's an excited object. The light guys down here, their masses squared are linear in the quark masses, and so they're qualitatively different. So if I move the quark masses around, things will change a lot. You think about a world in which the quark masses were so small that the cans, the etas, and the pi's had masses of 1 electron. What would that world be like? It would be a little different. Nuclear physics would be completely different. Jets would be somewhat different. But what if NF light were equal to 2 instead of 3? How different would that world be? What do you know?
You just get piles.
Well, obviously the particles that carry strangeness would be absent. So the cans, the eta would be absent. The K stars, which are excited cans, would be absent. A couple of these others, these variants would be absent. But really, qualitatively, it wouldn't be that different. What about NF light equal to 1? What if there were 5 heavy quarks and 1 light quark instead of 3 and 3? Very interesting case. So how does it work in QCD? In QCD, we have an approximate SU3 cross SU3, and then there's U1 baryon. So the SU3 rotates the right-handed UDNS, the left-handed UDNS, that's our SU3 cross SU3. There's a U1 baryon number, and then there's a U1 axial. And what happens to the U1 axial?
These numbers is broken.
It is not actually there. It's there in the action, but it's not there in the path envelope. The measure of the path envelope violates it, that's called an anomaly. So the U1 axial isn't there. So it's SU3 cross U1 cross, well, that's it. Yeah, the second U1 isn't there. Now, if I reduce the number of flavors to 2, it's SU2 cross U1 cross D1 that's absent. If I reduce it to 1 flavor, there's no SU anything. There's U1 baryon number, and then there's the U1 axial that isn't there. So U1 baryon is a symmetry that is not chiral. So there can't be any chiral symmetry breaking because there's no chiral symmetry break. So there's no pseudo-Goldstone boson, no Nambu-Goldstone bosons to be pseudo. There's nothing there. So if anything is 1, the theory is pretty different. There's no neutron or proton, right? You need 2 flavors for that. So you just have the delta. Which there's a delta spin 3 half which can have U. So that's different. There is a spin 1 state, there's a spin 0 state. Actually, there's a couple of these. There's a spin 0 state 2, I call it spin 0 state 2, I believe. The interesting thing is that the eta prime, which in QCD is heavy, it gets its mass by the anomaly, is the lightest spin 0 particle. And it's quite often heavy enough that the omega, which is the lightest spin 1 particle, cannot decay to it. So the spin 1 particle here, which corresponds to the rho omega over here, is stable. So I got a stable spin 0 particle, I got a stable spin 1 particle. There's stable both scalars and pseudoscalars, vectors and pseudovectors, a whole bunch of stable particles. Unless the mass of the A prime will go down if the number of colors gets bigger. Because when NC goes to infinity, the anomaly, which is proportional to 1 over NC, becomes less and less important. So as NC goes to infinity, we kind of do have a chiral symmetry, and then this does kind of become a pseudo-Goldstone after all. Which is, you can imagine, think about what jets would look like in this theory. One of the reasons we have so many particles in these jets, because we make a lot of rho mesons. Rho mesons are easy to make. There's 3 of them. Not just plus 0 and 1. I don't just mean there's 3 of them because they're plus 0 and minus. I mean there's 3 of them because they have spin 1. Right? So if you have a choice, you've got an up quark and a down quark, and you want to decide, if you're inside this complicated hadronization process, you want to decide whether to make a pi plus or a rho plus. Well, there's 3 rhos you can make because they're 3 spin polarizations. You make a lot of rho mesons. And then those decay to 2 pi's. So you get 2 pi's for the price of 1. In a world where you have more stable hadrons and they're kind of heavy, there might not be so many hadrons in a jet. Quite different. What about if NF white is equal to 0? No quarks. What do you make? You make blue balls. Down states of gluons. Okay. We know about these because we can simulate such a theory on the lattice. And there's, I forget the exact pattern of masses, but there's something like, these things are heavy compared to the QCD scale. Much heavy, about twice as heavy as the rho is relative to the QCD scale. There are no light hadrons at all. And there are at least, I think it's 7 or 8 of them that are stable, with various spins and completely different. So the jets we see in our world are not to be taken for granted. In fact, it's even worse than this, I'll tell you in a minute. Because in this world, you really don't have any jets at all. We'll get back to that in a second. One reason I mention this is that we could, of course, encounter in experiments someday a new force that might have a QCD like Lagrangian, but very different dynamics. One of the last really important things which goes on in QCD, which up to now I've taken for granted, Professor Catani has taken for granted, you probably take for granted, is that when you have a quark, it gets produced somehow in some proton-proton collision, it comes flying out with a huge amount of energy, you get a jet. Same with the gluon. And importantly, there is a notion of parton-hadron-jet duality. That the jet that you observe in a collision has a momentum which is related to the momentum of the quark that you produce. Now, they're not the same. They can't be the same. This object, this jet here, doesn't have 0 mass. It's made of a collection of hadrons and they're not all traveling in the same direction. So the invariant mass of that system isn't 0. So you know that the momentum of the jet is not equal to the momentum of the quark. But the momentum is large compared to the mass. The jet is obviously quite collimated, so there's a relatively small invariant mass compared to its energy. So roughly speaking, this is a decent approximation if you're not trying to do things very precisely. If you are doing things precisely, you should be able to at least estimate, certainly in some cases calculate a relationship between these two up to corrections of order like QCD or something. Well, that's not true in general. Even in theories that have this property, so why is that? Well, there are time scales involved in forming a jet. So let's look at what happens when you form a jet. All right, let's imagine the process, just take E plus E minus goes to quark A. Okay? So Q bar goes off this way, Q goes this way. Now let me imagine these are heavy quarks, like bottom quarks. So really what we're interested in is what is the dynamics going to be involving lighter quarks and gluons. So let's see, so this quark, let's follow this quark as it heads out. Heading out of the region of the collision, what's it going to do? Well, it's going to radiate gluons, because it can. which is another way of saying we never produce this quark exactly on shell. It's a little off shell, so it's got some room to radiate. And as those gluons radiate, as I mentioned earlier today. Okay? And if they can, if there are light quarks around, then there's some probability that, in fact, we call these capitals, just as distinguished. There's some probability of making a Q-Q bar pair, where Q and Q bar represent light quarks, things that are easy that we want to split into. There's some probability at very high energy that you could get the heavy quarks here, but let's ignore that. All right, so we have all of these things, and some of them are soft and are kicked out at random angles. Others are collinear and are traveling with the quark, and they can carry a substantial fraction of the quark's original momentum. And so some fraction of them pass into what we would like to call the jet region. Notice I have said nothing about hadronization. The jet is formed perturbatively. It is a perturbative object. Jets are not non-perturbative objects, they're perturbative objects. Well, they're perturbative, they involve resummation. You'll learn more about resummation from Professor Katani in the next couple of days. What I mean by that is, it's not sort of one simple diagram. But it's a recursive process. The quark emits gluons, gluons emit gluons, gluons emit gluons. You can sum that up, at least keeping track of the largest effects. And it's some sort of fractal process, by the end of which you have a jet of quarks, antiquarks, and gluons that are all traveling, many of which are traveling roughly the same direction, and all of which collectively have a momentum which is related to the momentum of this quark. And there's a few soft ones that get radiated off to the side. We're going to give a stray effect later. Okay, well, in a world that didn't have infrared confinement, for example, a world that just goes to a fixed point, this would just continue indefinitely. In fact, kind of what happens in QED, if you think of it. QED scatter at some incredibly high energy, we would get an electron which is surrounded by a bunch of photons, electron-positron pairs, and muon plus and minus pairs, and that's just the way it would be. But because of infrared confinement, we finally start to reach a scale at which the forces become very strong. And something's got to give, because these quarks and gluons cannot remain on their own. So what happens? Well, maybe glue balls try to form, and then glue balls decay to mesons, and mesons decay to other mesons. But basically, in the end, what ends up happening is that any gluon that's around eventually has to become a QQ bar pair, because the only stable things that you can make are made from quarks and gluons, quarks and antiquarks. So, along with lots of gluons, there's gluons flying everywhere. Basically, you start forming hadrons any way that you can. It's a complicated process. That's not perturbative. The issue is, how long does that take? Well, you know from what I said last time, or the time before, that one way to understand what's going on is you've got quarks that are separating from each other in physical space, and they want to be stuck together, but if they get too far apart, a little tube of flux will form between them, and then that flux tube will break. It breaks because once there's enough energy, you make even more quark-antiquark pairs. So, how easy is it to make such things? Well, the more light quarks you have, obviously the more types of pairs you can make. So, hadronization, the time scale, well, the rate, has an NF light. And it has a 1 over NC. Now, this is just the parametric dependence. I don't know what coefficient goes out right here. But I can tell you that if I kept the number of light quarks fixed at 3 and I took the number of colors to be very large, the hadronization rate would slow down. Why is this? Essentially, it's because the correlations within this flux between one region and another of color, quantum numbers that are floating around, gets less and less the more types of colors there are. And you've got to make sure you make a quark-antiquark pair that have canceling color, make a hadron. So if I have a quark over here and another quark over there, and I want to make a pair in the middle, such that I end up with two hadrons, I better make sure that the pair I make has a color which cancels the anticolor of that antiquark. The chance of doing that is only 1 over NC. The more colors I have, the harder it is to break the string. So, now what would happen if NC were really, really large, and NF light, let's say just 2 or 3, and so the hadronization rate is slowing down. Okay, so produce this quark-antiquark pair, they move apart, and they start to discover that they're not allowed to exist on their own. Well, so a flux tube starts forming, and it forms, I haven't really sort of emphasized it, but in a sense it's forming all the way along here. So there's a tube connecting the original quark and antiquark. It's a complicated tube. It's not strict. It's moved. It's very complicated in shape because of all these gluons. But basically, there's color correlations all the way along from the quark that I produced on this side to the quark that I produced on that side. And this string tries to break, but it can't. It's taking too long. What's it going to do? It's going to start slowing down. Right? And these things pull on each other. There's physical forces involved. It's a flux tube. It's energy. So instead of splitting, it slows down and turns around. So I produce my quark-antiquark pair. Before I know it, the energy's coming back in. So there's a transition which occurs. Just if the hadronization rate is too slow, it's no longer true that I get a bunch of hadrons and they're all heading in the same direction as the quark, carrying more or less the same momentum. Instead, the energy gets completely rearranged by the confining vacuums. And what comes out the other end may be some particles flying in all directions for all I know. It has nothing to do with the momentum of the original quarks at all.
Wait, can you repeat why it doesn't break?
It doesn't break because the hadronization rate is very slow because, and this was the premise of this scenario, NC gets really, if NC is really large, NF light is just fixed at 2 or 3. There's an NC which is large enough that eventually I don't get very effective breaking. Now there'll still be some breaking. But the point is that there's timescales involved. You can't just take this for granted. For early QCD theorists, it was not obvious which of these two things was going to dominate. People didn't know if there would be jets. Because you couldn't calculate this rate. Today, we know this rate, if NF light is 4 to 3 and NC is 4 to 3, is plenty fast. There's no reorganization at all, essentially. And that's why this is true. Why the jets that come out tell you about the momentum of quarks and gluons. But if NC were large, or if NF light were equal to 0, then you can't produce quark-antiquark pairs at all. And then you have to reorganize the color of one gluon with the anticolor of another gluon, and vice versa, which is 2 powers of 1 over NC. So in a theory with no light quarks, you surely have trouble getting jets. Hadronization rate is really slow. All of this is obvious in string theory. In QCD, you have to do a little bit of work, and the person who did the initial work was Toft, who showed how to count powers of NC, and Parisi, who had this notion of pre-confinement, this notion that in some sense things are already organizing themselves to be hadronized on the way in this process. And I think he was the one who emphasized NF over NC. So the things about QCD that we depend on for doing our measurements are absolutely not guaranteed. And in some sense, we got incredibly lucky. Now, if you're a formal QCD theorist and you would like to prove things about confinement, you don't agree with me at all. You'd like to prove something, I mean, of course, I'd like to prove something about confinement too, but the best theories in which to prove anything are theories of large NC. Because as Toft emphasized, when NC gets large, you have a nice 1 over NC expansion of what we're actually proving something. And you don't want NF over NC to be over 1. You want NF small, and you want n to be really large. Those are the theories in which you have to prove something as a theorist. But if you hope to do measurements, you'd be screwing this up if you went to that extreme. And if we didn't have this, how would we know what we were doing inside the program? It's crucial that we know something about what quarks and gluons do, because the jets mirror what the quarks and gluons do. And that's absolutely not guaranteed, and in a theory which was simpler for the theorist, experimentally, we probably still wouldn't know what we're doing inside the program. All of these facts, including this one, are relevant for potential searches for new physics. Because, again, we could run into a theory that has this property. Because NC is large, or because there are no light quarks. This isn't true. And so what we will observe, or we will begin to observe, that this isn't true, and this isn't true, and this isn't true. And so what we'll actually observe in the detectors won't look familiar to us at all, even though it's just another QCD-like theory. All right. Any questions? Okay, so we can take a deep breath and now proceed with a new topic. All right, so briefly, I spoke about the process of producing a W boson. Let's talk about simple processes. One of the simplest things you could do at the LHC is produce and measure the rate for example, Z boson. Or more generally, to produce a muon and an anti-muon, which are the easiest things to measure, and you just plot their invariant mass. So we're looking at a process where there's a muon, there's an anti-muon, and anything else. Jets, underlying events, you don't care. You just look at the invariant mass of the muons, and you make a plot, the number of events versus the muon anti-muon mass. This is very old data, for reasons that will become clear in a second. This is the data from 2010. And what do you see? Well, you see a falling distribution. There's your Z boson. What dominates here? What's the process that dominates here below the Z? How do you get those two muon pairs there?
Drell-Yan.
It's just quote Drell-Yan. Drell-Yan being Q bar going by either a photon or a Z off shell to mu plus mu minus. That's Drell-Yan by definition, and that dominates the rate down here. And then there's various other resonances. These are hadron resonances. Here's some of the ones I've got there. Right here, sometimes omega will, or rho go to mu plus mu minus. The J psi is a charm bound state. The epsilon is a B bar bound state. It's decay to mu plus. In fact, that's how they were discovered. Anyone have any idea why this rate isn't just going skyrocketing through the roof like that? Isn't it supposed to? The QQ bar parton luminosity kept going up. So why is this thing turning over? Hint. It has to do with the trigger. Anyone have any thoughts, ideas, guesses? The point I want to make here in emphasizing this is that, especially at low energies, you have to remember that the trigger is a filter. It's throwing out lots of events. So your perturbative calculation of what you expect by just writing the particle distribution function is integrated against the theory calculation is affected by the fact that they don't keep all their mu plus mu minus events. They can't. For example, the number of J psi's produced at rest in a process like this, where what you actually do is QQ bar goes via gluon and makes a CC bar pair plus maybe an additional gluon to conserve color, and then that goes to mu plus mu minus. Well, the rate for doing that, where the CC bar pair forming the J psi is at rest is absolutely enormous. They can't possibly afford to keep all those. In fact, most of those muons don't make it to the muon system because the J psi has a mass of 3 GeV. The muons have an energy of 1.5 p, a transverse momentum of at most 1.5 GeV, and those things will curl around. They won't even make it to the muon systems. They don't measure those. And even if they did, they'd have to throw most of them out. So the J psis that you're seeing here are actually from a case where the J psi is produced with a substantial momentum. So the muons come out with a substantial momentum, and there's a jet on the other side. It's not all the J psis. It's the J psis where the muons are energetic. And indeed, that's the way this is done, that you're selecting events generally where the objects you're looking at, the muons, say, photons, in the case we'll study in a minute, are relatively energetic, which means you're throwing out the substantial number of ones that are produced at relatively low momentum. And so you get a shape which is determined not by the physics, but by the combination of the physics and the trigger. The trigger shapes your low momentum events. As a result, you see all sorts of strange effects down at low energy. You just have to understand that's probably what comes. Okay, this is very simple, right? The Z boson in the case of B plus and minus, you just compute the invariant mass of the final state, and you're done. Well, we know another process, another particle that's good for. Not the W, because you don't measure the neutrino. But it's pretty good for the Higgs. So let's study that. The Higgs decaying to 2 photons is one of the classic ways for it to be searched for. And what I want to do now is talk you through the basic issues that go into that part of the discovery. So, first we have to know about how you produce the thing, and then we have to know how it decays. How do you produce it? Well, here are the 5 processes at which, at the LHC, well, whether you call them 5 or 4 is kind of up to you. But basically, these are the 5 gauge invariant separable processes. And I've put a line here at 125 GeV, but you notice that no matter what the mass of the Higgs, we're going to be talking about these 5. What are they? Well, the curious thing, of course, is that the largest way to produce the largest cross section for the LHC to produce Higgs boson comes by a loop effect. It comes by this process. Some quark running in a loop couples to the Higgs boson and also couples to gluons. Why is this so good? Even though it's a loop effect, the loop effect, of course, means there's a significant suppression of the coupling, the loop, but there's lots of gluons. Huge gluon luminosity. And that outweighs everything else. What's the next most popular process? Well, it's this one, known as vector boson fusion, or sometimes PP goes to QQH. That's not a typo. It's not QQ bar H. Remember I mentioned briefly that the particle luminosity for quarks is actually, for 2 quarks is actually interesting. It's because of this, and this process and processes like that. V here stands for W or Z. What's an example of a situation where quark-quark is inverted? Well, I can have an up quark come in, spit off a W plus. I can have a down quark come in, spit off a W minus. And now, from the fusion of a W plus and a W minus, I can make a Higgs. If these were 2 up quarks, I could have 2 Z's. 2 Z's confused to make a Higgs also. So, even though we have proton-proton, we can make Higgs bosons even without gluons by this one. And it's substantial, as you see. It is, in fact, the second largest. The third largest and fourth largest in this plot involve the same process, same type of process we would use in E plus E minus plot. We produce a vector boson off shell, and that then turns into an on-shell vector boson and a Higgs. That could be a W plus, W minus, or a Z. By the way, since the LHC is a proton-proton collider. It means it has an initial state which is charged 2. The rate for producing W plus Higgs and the rate for producing W minus Higgs are not the same. That asymmetry is actually useful sometimes in measurements. And finally, we can produce from blue-blue, or more general initial states, a pair of quarks, quark-antiquark pair, and Higgs. And those are our 5 options, 4 options. Now, it's kind of obvious that in this process, the only one we really care about is the top quark. Right? The top quark has a Yukawa coupling which is basically 1. That doesn't mean it's strongly coupled. The strong coupling scale would be y top squared over 4 pi, and that's a 10. Perturbation theory is fine, but the Yukawa coupling which appears in Lagrangian is about 1. The bottom quark, you're already down by a factor of 30, and then 40, 50, what is it, 5 GeV, 20, 75, and you square it. It's a big price. So unless you have some enhancement of this coupling as you can have in models that have 2 Higgs deltas, or more complicated Higgs sectors, the only one you worry about, sort of in the standard model, is where this quark is the top. So TT bar H is an important process, but because the top quark is heavy, that suppresses the rate, which is why this is a bit lower than these guys. It's still going to be important for measurements, and of course we're interested in measuring this coupling. So people do want to measure this. Okay, so in this process we measure the Higgs top coupling. In these 2 processes we measure the coupling of the Higgs to the WZ. What about here? Well, there's a calculation to do. And here is a preprint. You'll get these slides, so you don't have to write this down. There's a preprint, I don't even know if it was published, which gives a nice pedagogical step through of the entire calculation. It's the only place I've ever seen it. And it's a function, basically sum over the contributions of all of the quarks. And it's a function for each quark of tau. And it's just basically the sum, this thing gets summed over all the quarks. Tau being 4 times the mass of the quark squared over m Higgs squared. And there's sort of two different regimes. There's actually a transition between them. If you're talking about a very heavy quark, this function here is substantial and goes to some constant. But if you take the bottom quark mass, or the chart quark mass, this is very small. And when tau is very small, this goes to 0. Not obvious, but it is true. And what that tells you is that the contribution of this loop gets a big contribution from the top quark, but again, from the light quarks, there's no contribution. No substantial contribution. So again, we're only really looking at the contribution of the top quark, and therefore we are again measuring the top quark coupling. Now that's of course a statement that in the standard model, this coupling and this coupling are related, but if you're beyond the standard model, something else might appear in this loop. And could increase or decrease, if there's destructive interference, the Higgs production process. So the fact that this is a loop is interesting in many different senses. One of them is makes it sensitive to physics. And therefore, if you don't see deviation, it rules out lots of physics. Okay. Now, very importantly, the total cross-section, which is given here it is at 7 TeV, here it is at 8 TeV, here it is at 14. Notice when I go from 8 TeV to 14 TeV, the Higgs cross-section jumps by about a factor of 3. The same luminosity, just increase the energy from 8 to 14 buys me a factor of 3 in statistics. Partly because there are more gluons of low energy, well, largely because of that. So if I increase the energy, let me say it better, if I increase the energy of the machine, the X value that I need to produce the Higgs is now smaller, and there's more gluons down there. Notice this error bar. Substantial. 15%-ish. Where does this come from? This is a next to next to leading order plus even the next to next to leading log, for those who know what that means. It's trying to do even a little better than next to next to leading order. QC plus keeping track of electroweak corrections. Well, this is a calculation. Here's the QC part of it. This is the calculation of the Higgs production rate. It's actually scaled in the same way, so it's the same cross section. Right, of order 20 picobarns at 8 TeV, and it's going up to about 60 picobarns at 14 TeV. Here is what the leading order calculation gave you. That is to say, you just write this graph and nothing else. And now you account for the fact that gluons can be radiated off the initial state. Or this gluon could have come from a quark that radiates it. And the answer jumps by a factor of 2-ish. Now, this is the 1 sigma error bar that you would guess by varying the factorization scale by what seems like a reasonable amount, right, or the normalization scale by a reasonable amount. This is what you think your 1 sigma error bar is, your best guess as a theorist, and what do you know? The next correction is outside it. So you do it again. You say, well, I'm pretty sure it lies in this region. You do the next calculation, and whoop, it's up again. The Higgs calculation, Higgs production calculation, is one of the least stable calculations that we've come across in perturbation theory. And no one can tell you precisely why. People will argue over it. There are arguments as to why it's more unstable. Having gluons initial state is part of it. In the loop process is part of it. But I don't think anybody could have told you to guess this. Of course, it's in our favor. We make 3 times as many Higgs bosons as we used to think back in the old days. But it also makes you wonder, are you sure that that's the right error bar? So, be a little careful about how we interpret the results. Any questions about Higgs production? Okay, the converse, of course, is Higgs decay. Here are the various branching fractions. Again, drawing a line at 125 GeV as best I can. Bottom quarks are the most common. Higgs goes to bottom quarks the most common. Then W's, gluons, taus, charm, photons, Z photon, muons. Right, where's this all coming from? And what sets the pattern? Why does it look this way? I mean, it's pretty wacky plot. Lots of stuff going on. Well, at 125 GeV, the basic processes are the Higgs can decay to fermions, in which case that rate has a Yukawa of the fermion there. And since the top quark is not accessible for a Higgs of this mass, obviously what is going to dominate is the bottom quark, but that's a pretty small couple. So the Higgs has a small width when it is light. And that's seen in the lower quark. A light Higgs boson, whose mass is up here, has a width that's small by almost a factor of 10 to the 5. That's quite important in the context of new physics, as I'll come back to later at the very end of the course. Okay. Now, maybe it's easier to start at this end. Let's start at this end. Supposing the Higgs were very heavy, what would it do? Well, it would decay to the heaviest things around, the W's, the Z's, and the top quarks. Here's the top quark, TG bar. Why isn't that biggest? Okay.
Too light.
No. This is for a Higgs of 600, 700, 800 GeV. So I'm out here, the Higgs is really heavy. Why is the top quark, why is the branching fraction of the top quark less, significantly less than the branching fraction of W's and Z's?
Because the top quark is heavier than the gauge bosons.
Top quark is heavier than the gauge boson, so therefore it has a larger coupling to the Higgs. Right? It gets its mass from the Higgs, so you would think the Higgs couples the top quarks with a coupling constant of order 1. The Higgs couples the W and Z bosons with a coupling constant of about half. So why do I get this pattern?
Phase space.
Sorry?
Phase space.
It's not phase space. The reason is that, I've already mentioned that this is a very special coupling. right? An ordinary scalar does not have this coupling. And in particular, hidden in here, there is a factor of the expectation value of the Higgs. This is really a Higgs-Higgs-WW coupling with one factor of the Higgs value. It's really a dimension-free interaction, not dimension 4, which makes it relevant in a technical sense, and it gives you an extra factor, which makes the width bigger than you naively guessed. Another way to say this is that the W's and Z's have hidden inside them the longitudinal W's and Z's are really part of the Higgs, and to make the Higgs heavy, you have to make the Higgs self-coupling big. That's how you do it. Well, if the Higgs self-coupling is big, then the Higgs coupling to the longitudinal W's and Z's is big, and that gives you a big width. Okay? It's because really the coupling of the Higgs to these things is not G weak. It's really the Higgs self-coupling. And it's growing as the Higgs mass goes up. So the top quark never catches up. Okay, obviously if you get below the top quark mass, which is twice the top quark mass here, then the Higgs stops decaying to those things. So in this range, the Higgs is kind of boring. Mostly it behaves with W's and Z's, and you barely get anything else, 10 to minus 3 for even bottom quarks. And then as you get down in this range, things start to get really interesting, because first, you can't make Z's on shell anymore. The Z is too heavy. You can't make W's on shell anymore, because the W's are too heavy. So as you head into this region, the only thing you can do involving the W and Z is to make one real one and one that's off shell, one that's virtual, and decays to a fermi and anti-fermion pair. Leptons and quarks, neutrinos. Okay, and that takes care of bottom quarks, W star, taus, charm, those are all of these two types, and ZZ. Right? ZZ is up here. Now we get down here and we find another very important process, which is the one where I produce two photons. And what appears in this loop is anything that couples to the Higgs, it carries an electric charge. So quarks, leptons, and W bosons. And it turns out the W boson is very important. So the top quark contributes for the same reason as the calculation I showed you a slide ago. It's the same type of calculation for photons as for Z's, and so for photons as for gluons, and so therefore only the top quark matters among the fermions. And then you have to do a non-trivial calculation involving the W boson loop, and that turns out to be bigger, of opposite signs, so there's partial cancellation. W is most important. So again, you're quite sensitive in this process to the presence of new phenomena. If there are new particles running in this loop, it could change the rate for this process, as well as the rate for this one. Okay? And so, the reason that the Higgs width is so small in this range, and not up here, is that up here, you're decaying to W and Z bosons via the W and Z coupling constant, which is, well, really the Higgs self-coupling, or the weak couplings, and weak interaction couplings, and those are order 1. When you get down here, everything's suppressed. You're decaying to bottom quarks or something later, and you've got a small coupling. You're decaying to W's and Z's, but you're off shell, it's a 3-button decay. Or you're decaying via either the gluons or the photons. Everything's suppressed. The width is really small. It makes the Higgs very, very sensitive to new decay modes. If you add something else to the theory, the Higgs maybe can decay to, even if it has a very small coupling, the Higgs will do it. In fact, it was certainly possible to have a Higgs that's completely invisible, would never decay, basically with 99% of the time would decay to something you couldn't see, even for this mass range. Didn't turn out to be true, but... Alright. Yeah?
Why is it that going up again?
Yeah, so that's a good question. So what happens here is that you go below the ZZ threshold, but the W's are still on shell. So you notice that the rate for W's goes up. Then when the W's go off shell, the ZZ comes back up again. These are branching fractions, so once you suppress the W, everything comes up relative to that. And that's why, as you see, the Z comes up, but so is everything. Everything else is also coming up very quickly. Good question. All right. Here's an event in which two protons collided, giving you an underlying event that's a bunch of crap. Maybe a little bit of activity on this side, and two objects that have no tracks and have energy in the electromagnetic calorimeter of the CMS experiment. In other words, two photons. It's probably not Higgs, but it's a candidate. So how are we going to find Higgs? Well, at least in this channel, we're going to do it exactly the way we look for the Z. We take all the events with two photons, photons that are nice and isolated, don't really look like, they might maybe be jets, they don't look like remnants of pi zeros. They have to be energetic enough so that we even trigger on them. So let's say one of them has to have energy of 40 GeV and another has to have energy of 30 GeV, otherwise the backgrounds are just way too big. So that's a typical trigger threshold people want to use. 40 and 30 for two photons, maybe better than that, maybe 20, something. All right, so we take all the events that have such photons, and we just plot their invariant mass, and we look for a bump. And that worked in the case of the Z, right? You couldn't miss it. What are the backgrounds? So we're looking for blue goes to the Higgs, which then, sometime later, decays to two photons. And the biggest background is the one you would guess. QQ bar goes to two photons. That's not a small rate. But of course, this is kinematically resonant. This is kinematically continuous in mass. So you should be able to see this as a bump over that background as long as this background isn't too big and this bump is big enough. And as long as your resolution, as long as you can measure the invariant mass of the two photons very precisely. And if I have a bump over a background, and I don't measure it very well, it's just going to smear out, and I won't be able to see it. So if I have a bad measuring device, I can have a nice narrow bump, it's not going to look narrow, and you won't be able to find it. So a key, both at Atlas and CMS, is to measure photons with very high precision. 1% sort of precision in the energy of these particles. And much better than that in the direction, if possible. 1% of what we got here. Even 0.5% can do it. 1% is probably... and of course, the invariant mass of the two photons has a resolution. The invariant mass of the two photons is the sum of the momenta, sum of the four momenta quantity squared for the two photons. So if I have 1% resolution on both photons, I have 1.5% resolution toward 2% resolution on the pair. So you really, to get good resolution on the Higgs mass, both to be able to identify the peak and be able to measure its location, you need really good measurements. Part of why the electromagnetic calorimeters in both machines are really, really carefully done. Okay, this is a big background. Here's another. Glue goes to glue. Fake gammas. Well, maybe two fake gammas isn't that common, but you could certainly have one real photon and one jet, and second jet, and the jet fakes a photon. Only happens 10 to the minus 4 at the time, but it matters. But if you're an experimentalist, there's things you can do. You can be clever. You think of all sorts of different ways to reduce this fake rate. This is called a reducible background, because in principle, if you have a better experiment, you can get rid of this problem. You just reduce the fake rate until this is no longer a significant contribution. And that's essentially what happened. It's still an important contribution, but it's not dominant, because of how well they built their experiment. This is an irreducible background. Nothing you can ever do will remove this, because they really are photons. This is literally the same as your final state. So again, reducible and irreducible backgrounds. And it turns out in this experiment, this is the most important. And so you might say, well, okay, it's really important for some theorists to calculate this in leading order, next leading order, next leading order, and no. Because you're looking for a bump. You just measure the background. You don't need to know what it is. You're just looking. You look at your data, and your data comes down, and it does that. And I don't need to know what the background is. I just draw a line through it. This is called a sideband analysis. It's self-calibrating. What happens over here, what happens over there, tells me what the background should have been there. If I see something else, well, it's a discovery. So it's a great measurement. I don't have to know the background, I just have to measure it. And here's the data, and there's the Higgs. Everyone see it? This is the data now. Can you imagine what it was like when the discovery was announced with 1/3 this much? Or when the hints were first announced in 2011, and people were jumping up and down saying, oh, they've seen it, they've seen it. This is what the data, a sixth of this data. It's all bouncing all over the place. You see the Higgs? Well, it's really easy to see the Higgs. See, there it is. When you draw the lines in it. There's a real lesson in this. And, oh, it's really easy if I subtract this fit line with the Higgs in it from Higgs, it's not the Higgs, but a Gaussian on top of an exponential, and I look at the differential. Well, boy, how would you miss that? Okay. Do not let people swindle you with your data. Always go back to what they're really working with. Because your brain will deceive you when they redraw things. When they put lines through things, you will see stuff that isn't there. Very important lesson for theorists. Don't take this stuff for granted. Experimentalists, the great experimentalists are really amazingly good, and the great experimentalists have made mistakes. Carlo Rubbia won the Nobel Prize for the discovery of the W and the Z. Half the W events weren't W's, they'd be more. The discovery of the top part that he made at the top part before UGB wasn't correct. The discovery of supersymmetry is also not correct. Okay? You cannot take these things for granted. He was a little bit overzealous. Not everybody is so overzealous today, but every generation has its mistakes to make. So, if this is all we had, I'm not sure how confident we'd be. And certainly a few months ago, back when the discovery was announced, I was not convincing at all. Here's another way to look at the data. It's always a good idea. So there's some data on the left, there's some data on the right. You see the bumps on the right? It's the same data turned upside down. Okay? If the bump that you can see right side up is no more convincing than the bumps you can see upside down, it's probably not very convincing. It's just barely enough to give you something. There's something happening here which, that looks like a bump. You really have to train your eye. Your brain is not designed to do this. You really have to learn. Your brain is designed to find patterns where none exist. And your brain will do it again and again and again, no matter how well trained you are. You have to trust in statistical methods, which can help you figure out how likely are you to be confused by what you think you see. Now, the statistical methods that people use to analyze this data actually are even more important than I've emphasized so far, because this data is already processed. In fact, these people are trying to make a discovery as early as possible, because Alice doesn't want CMS to make it before CMS, before okay. Nobody wants to be second, right? So they're working as hard as they can. So what do? They take all their data and they say, well, some of these events are really well measured, some of them are not so well measured. So let's divide them up into categories. For example, one thing I didn't mention yet, but is important, is that a photon, it said, is something that doesn't leave a track and puts energy in the electromagnetic calorimeter. Except for the fact that a photon sometimes can convert into an electron-positron pair as it passes through a beam pipe or some piece of the track. So you now get a pair of tracks very close together, one electron, one positron. And so there is some activity in the track. So you have to be able to distinguish a converted photon from an unconverted photon. Sorry, from an electron. So converted photons are not measured quite as well. The resolution on the energy is quite as good. So let's take the events that have one converted photon, put them in this category. The ones that have two converted photons, they're in a different category. The ones that have unconverted photons, well, some of them go in the center of the detector, in the so-called barrel. And some of them go towards the outsides, the forward calorimeter, which isn't quite as good at making the measurement. So let's divide it up into those categories. Sometimes both photons are in the center, but one's in forward, both are forward. And we'll do the best analysis we can on each one of these, and then we'll pile them all back together in some weighted way, and that's what we'll do. Do you think I understand what they did? Am I convinced that most of them understand what they did? No. I mean, the experts do, of course, understand it, but it's very complicated. Now, is there a particle there? Yes, I'm sure there's a particle. Not trying to convince you of that. But I wasn't sure of that a year and a half ago. Two years ago. A year and a half ago it was pretty clear, but not because of this data. Before I move on, let me show you some plots. Here's a plot of 9 experiments that saw particles. Anybody know what this particle is? 1540 or so MeV to atom or something. This is called a pentaquark. It's a big discovery in 2003, 4. And it wandered around from 2003, 4, 5, 6, 7. All these different experiments saw it, showed up in all sorts of plots, and then they threw a big experiment at it at JLab, and they saw everything. This doesn't exist. 9 doesn't exist. Okay? Be very cautious. Especially when people are looking for something, A, they believe is there, and B, they want to be sure not to be the one that can't see it. There's a tremendous amount of human bias in experiments, and this is a great example. And so back in December of 2011, it was far from clear we weren't doing just repeat this. Now, are there any questions about the photons? I'm going to move on to something else. So Higgs related. Actually, let me make a remark. I didn't emphasize this. Look at the numbers. Okay, we are looking at in each, by now, with all of this data from 2011 to 2012, each one of these bins, which is 2 GeV here and 1 GeV here, 1.5 GeV here for CMS analysis, they have thousands of events, and the number of events that are from Higgs bosons is in the hundreds. Which makes sense. We're producing 500,000 Higgs bosons in each of these experiments, of which about 1 in 500 decays to 2 photons, and you don't pick all of them up. So that's roughly the right number. The background is huge. It is mostly from this process. So this is an experiment, this is a measurement where you use large background and a small signal. But the signal is still substantial, hundreds of events. The next signal is from Higgs goes to Z star. So at least one Z is offshot. They can both be offshot. And the rate for that was pretty big. You may remember that was like 1%. But it's not useful to you unless the Z decays to something you can measure. If the Z decays to quarks, you're going to be completely drowned in background. No. So what you're waiting for is those magical events where you get a lepton pair on both sides. And by lepton, I don't mean taus. Because taus decay with neutrino, you don't measure them so well. Leptons to an experimenter usually, except in special contexts, usually means electrons and muons and their antiparticles only. So 4 leptons, meaning 2 leptons and 2 antileptons, meaning E's and U's only. And here is an event which contains a muon and an anti-muon, I don't know which is which, an electron and an anti-electron, again, I don't know which is which, and junk from the underlying event. These events are quite rare. What's the background? Well, the background, I'll talk about the background in a second. By the way, there's something funny in this graph. Notice this track goes out to the edge, this track goes out to the edge, and then it's extrapolated out to the muon system. This one goes out to the edge, it's extrapolated to the muon system. Here you can see that the electron is left some electromagnetic energy. Why does this track stop here? What does it tell you? Hint, it's about geometry. Okay, the tracker looks like this. If the electron goes out, the track goes all the way from the center to the edge. But if it goes this way, which is the edge of the tracker there, that is an electron swung either forward or backward. It didn't make it to the outside of the tracker before it left the tracker. Okay. Ready for the data? There it is. Wow, look at that! What's that? What's this? These things. All right, so I deliberately left the numbers out so you wouldn't know. Okay. This is the onset of real Z-boson pair production. At some point, you reach 192 GeV, you start producing two Z's, and the Z's decay sometimes to leptons, and there's a fall off because of carbon distribution functions, and also because the actual rate falls off with energy. But there's a threshold, and that threshold is a real physical threshold, and you see it here. Now, below here, what you're seeing is, again, standard model production of one on-shell Z and one off-shell Z, or one on-shell Z and one off-shell photon. It's Drell-Yan on one side and a Z on the other. And that's this region here. And then there's this bump. If you had run a Monte Carlo, that's say you ran one of the computer programs that's available for doing simulations, and you ran it back in 2007 or 8 or any time before, this bump would be. Which is another lesson, which is don't trust your Monte Carlo, trust your brain and your Monte Carlo combined together in the most intelligent way. What is this? This is a Z-boson. Wait a second, the Z-boson doesn't decay to 4 leptons, does it? Sometimes. This is from UQ-bar, goes to a Z, the Z goes to a lepton and an anti-lepton, and one of them radiates a photon, which splits to a lepton anti-lepton. Bingo. That's not in your Monte Carlo, it doesn't mean it's not in physics. Computer programs only know what you know. What you know. Totally left it. But it's great because it's a beautiful calibration point. Now we can really check with this peak that the measurements of electrons and muons, we have to measure those really precisely too. Right? We want to be able to measure those to 1%. Are we succeeding? Well, this gives you an opportunity to check. If this peak looks wrong, then you know something's wrong with your measurements of electrons or muons or something. You can track down which one is problematic. The fact that these things agree with what is now a correct standard model prediction for this rate is a good sign. And so then your eye is drawn to the thing that doesn't agree. Because what's in blue and what is in red is the standard model of background prediction. And, well, there's that. And there's this, and, well, maybe, you know, is that a statistical fluctuation? Is that not a statistical fluctuation? Well, you know, neither of these experiments by itself is convincing, perhaps, but you take the two together, they have a bump in the same place. That's pretty convincing. And it's in the same place as the bumps in the photon. So certainly when you combine the fact that both see a bump in photons and both see a bump here, where this is very different. This is a low signal, not many events. Like this is 20 events in that bin. 12 events in that bin. They've binned differently, so that's why the numbers are different. The total number of events here is in the tens, not the hundreds, from the signal. But the amount of background is small. Background here is of order 4 events per bin. Here it's 5 events per 6 events per bin. So they're very different in character. Here you actually do have to kind of predict the background because you can't really draw a line through this. It's too bouncy. So this does rely on Monte Carlo. You have to worry about whether they got it right. But on the other hand, this is big enough that you're not really worried too much. I'm pretty worried back in 2011. 2012, by the discovery, these two things together with the 2 photon measurements were just barely enough to be convincing, at least to mine, just barely. Even though both experiments said 5 sigma. If one experiment makes a mistake, it can say 5 sigma isn't incorrect. 5 sigma is the gold standard for 5 standard deviations, is the gold standard for what particle physicists can think of as convincing evidence. Well, if I had taken those pentaquark plots and combined them all together, it was much more than 5 sigma. And you have to think too. If both experiments give you rather unconvincing bio sigma, but they both give you 5 sigma, okay, it's probably convincing, but only because one is checking the other. You just had one experiment that said 5 sigma. I don't know. All right, here's the plots they actually show. Again, they always show you this plot with this big peak here to draw your eye. I removed it so you wouldn't be confused by it. So there's the real data with the standard model backgrounds only. And there's the data with an attempt to fit a standard model Higgs boson, so that's the height and the mass being selected at 125, 126 in this case, 125 in that case. You notice that the data is a little bit on the low side here. It's not a big deal, but just it'll be relevant in a second. So let me put all of this data together for you. Again, this is the full data set that we have so far. This is Atlas, this is CMS. The color coding is confusing, so you have to actually read it. This is, so let's see, this is the Higgs mass as measured from the data. This is the signal strength relative to the standard model expectation for a particle of that mass. Okay, the Higgs signal strength depends on mass. If you think the mass is 126.5, you have a prediction for how many gamma-gamma events you should have, and then they would sit here. This is one standard deviation in solid. This is 2 standard deviations in dashed. If you see things that deviate by 2 standard deviations, you notice. If you see if they deviate by 3 standard deviations, you start to get concerned. If they deviate by 5, then maybe you're convinced of something. Here is the Atlas measurement of ZZ star. Here's the Atlas measurement of gamma gamma. Again, notice a couple things. First of all, they're both a little high relative to the standard model. They also give different masses that differ by 2 GeV, which is more than the 1 GeV resolution that they sort of claim to have, which is why you see that at 1 sigma they don't overlap. Another way to say that is the measurement of the mass given by Atlas from gamma gamma is more than 2 sigma away from the measurement by Atlas of ZZ star. Oh, and there's been all sorts of discussion. You know, data does funny stuff. I already showed you that in the pattern cortex. Data will do funny things, always. And when there's 20 different funny things that can happen, one of them is going to happen. Okay, this is the funny thing that's happening when it happens. Your mass measurements are off. Yes, they're also a little high, but barely by 1 sigma. Here's the combination, and you see that Atlas's measurement of the rate for Higgs production is only, for Higgs production times these 2 branching fractions, is only about 1.5 times, sorry, 1.5 sigma and 1.5 times what's expected from the standard model. 1.5 sigma happens every day. So the discrepancy here is between the mass measurements, and that's probably some fluctuation in one or other measurement, or even a little mistake somewhere, and this will get settled out over time. Here's CMS, and you see they don't have this issue. Their gamma gamma is in green. Please remember that, because I'm going to combine these in a second. So their gamma gamma is in green, and their ZZ is in red, unlike this plot. And here they only show the 1 sigma contours, but you see that they're completely consistent with each other, both in mass and in rate, and they're consistent with the standard model rate for a particle of 125.6 GeV. Now, I'm going to show you what the data looked like a year ago, when only a little more than a year ago, when a little bit less data was available. And compare these two. Now, their plots are lined up, they're different sizes, so it's a little confusing, but basically they're lined up. So I'm going to switch between them. Just look at the curves. What are the big differences you see? Well, perhaps when you see that the Atlas results earlier, they were a little further apart in absolute range, but actually in terms of the statistical significance of the differences between them, it's not that different from what it was before. It was about 2.5 sigma from here to here, and it's still 2.5 sigma. It's no big change from there. The real difference you notice is in the green curve on the right. CMS used to measure the gamma gamma rate that was high, just like Atlas. Then they did a reanalysis. They tried to do things better than they did them before. and it went, oops, and it went down by a lot, to below the standard model prediction. These data are correlated. 2/3 of the data that was used in this analysis was used in the previous one. Half. So why did I get such a different result? I don't know. Maybe that's just the way statistics can play with you when you try to take your events and you divide them up into all these different categories and you measure them all separately and then you put them back together again. Every generation has mistakes or curiosities or subtleties that it runs into and thinks, okay, we're better than the previous generation, we know what we're doing, we're not going to make the mistakes they made. But then they go ahead and they try something really hard for them. And they get their own set of mistakes, or challenges, or problems. Nobody knows what's going on with that one change. But should you be worried about it? I mean, we're going to get more data. This is all going to get settled. It's all just to say that when theorists were jumping up and down about the fact that Atlas and CMS both were seeing an excess of gamma, and tons of papers were written. This is making a lot over 1.5 to 2 sigma effects and combining two experiments that maybe you should use cross-checks on each other rather than just things you combine. I'm always very conservative about this, and I think the data and history support that. But other people are happy to write lots of papers about it. It's up to you. Okay, so finally let me put these together. So again, hard to read. Here's the here's the CMS gamma, here's the Atlas gamma, here is the Atlas ZZ, here is the CMS ZZ, and there's a particle there. Okay, what is its mass? I don't know. It's somewhere in the 124 to 126 range. Its production rate might be a little high, maybe Atlas is right, but don't forget the error bar on the production rate. It comes to that next leading order calculation, you still having a 15% error bar. It could be that this rate really should be here, and then it's not a 1.5 sigma deviation to 1 sigma. Okay. Any questions about the Higgs discovery? Okay. In that case, let me spend a few more minutes on on processes which don't have a resonance. So I'll just try to place for a second so you can see. This is a process in which in Atlas where a W boson is probably produced. It's quite similar to one I showed you before. There's a muon traveling out through, you can see here it is in the tracker, here it is the technical muon system. And if you look on the event head-on, you see the soft tracks of an underlying event. You see a muon going this way, and that dot line means that there was missing momentum, missing transverse momentum, or missing energy measured, pointing in that general direction. So it's consistent with having produced the W boson, more or less the rest. The trigger in this case is just a single muon. And you basically just look for single muons with energy higher than 25, 30 GeV. This is one of them. Okay, so now unlike the Z boson, which gives us 2 particles, or the Higgs boson, which gives us 2 or 4, or just reconstruct the resonance, this is not the case here. And again, that's because we don't know the neutrino momentum. We only know the transverse part of its momentum. So, what can we say about W boson production? Well, one thing we can do, which let's think fairly naively first and then work our way out. Yeah, go ahead.
Sorry, we not talk about volume of set stuff.
I did say it in words. Yeah, just ask me afterwards. Let me know your comment on that. It's a small one. So let's just be a little bit naive. W bosons, like pretty much anything else, are most easily produced, when they're produced, at rest relative to the beam height. Why is that? Well, if they're produced with a lot of momentum relative to the beam height, that means I need more energy in the initial collision. Right? If they produce with a lot of energy, then they're recoiling against something with a lot of energy. More energy means that the center mass of the parton center mass frame was bigger. that means that I have to go out at farther larger s hat, and that means the Parkin distribution functions, more precisely the Parkin luminosities, are falling. So I pay a price. It's always easier to produce something near threshold because it takes less energy and there's just more partons in the proton at lower energies. So, when I produce the W boson, sure, there'll be some probability that the W boson has a kick sideways, but the majority of them are going to be not moving very much relative to the beam pipe. They may be moving down the beam pipe, they may be moving up the beam pipe, but they're not going to be moving very much off the beam pipe. Okay. Now, what that means is the following. So here's a W boson. It's been produced, it's moving along the beam pipe in the same direction. Let's go to its rest frame for a moment. And it's now going to decay to a muon and a neutrino. Okay, one way it could decay would be like that. Or it could decay like this. Or it could decay like this. Now, of course, in the rest frame of the W, in every case, the energy of the muon is basically half the W mass. But we don't measure that, because what we measure is in the left frame. So what we're going to actually observe is a muon going off like this, a neutrino that we only know went in this general direction. We don't know whether it went this way or this way or this way. So we don't know if we're dealing with this picture, or we're dealing with this picture in the W rest frame. Is that clear? It's important. What we do know, however, is that if I look at the momentum that is transverse to this line, the PT of the muon, which is mw over 2 times the sine of the angle in the W center mass frame, that PT is the same in the left frame. Right? It's Z-Lucent current. So if the W's were produced predominantly at rest, the PT of the muon could be 0 up to mw over 2, but no larger. So that would suggest that the W's are produced at rest, I should see a plot which looks something like this. And the W mass being 80 GeV, it should stop at 40. Now, of course, it won't quite do that. Can you give me a couple of reasons why it won't do that? At least two very different reasons. I mean, it could have some different shape, but it won't even stop at 40. Why will I see things above 40?
W might have high PT.
So, one is the W can be moving. So I expect a tail that comes from the fact that sometimes the W is moving. We have to actually calculate how big that tail is. We can do that. What's another reason? Even if the W's were not moving, if they really were at rest, there'd be another effect. The W is a width, right? The W is a lifetime, and that width is about 2 GeV, not negligible on this scale. All right, well, here's what the data looks like on the left. It's not too bad. This is the transverse momentum model happens to be electrons, the same idea, right? Here's 40 GeV, and that's what it looks like. By the way, any guesses why you don't see data down here? Why didn't they show you data down below 20? Trigger. They don't trigger on electrons down there. Even in this data, which was back a long time ago, now the triggers are creeping up and creeping up and creeping up, maybe even creeping past it, for the reasons I showed you earlier. Okay. So, that's not bad. It turns out, though, there's a better variable to use for making a prediction, which is to use something called transverse mass. And I will explain what that is next time. Where I'm going with this is, we're learning here how to deal with particles where we have neutrinos, and therefore we don't have all the information. Well, the Higgs boson can go to W star and give you two leptons, or lepton, anti-lepton to be more precise, a neutrino and an antineutrino. You have to make some measurements there too. So looking for Higgs boson W star is a lot harder than Higgs boson ZZ star. You don't get that resonance. But you start using methods that are something like this. Much more sophisticated, much more difficult. They're not that sensitive to the mass. And that's why the discovery wasn't made using them, but they're still important measurements to make. Good. Any last questions before we quit?